Hello, everybody at IMO 2025. My name's Simon Coyle, and I work as Head of Philanthropy at XTX Markets, which is an algorithmic trading company headquartered in London. Now, I can't travel this year, so I'm dialing in from cloudy Northern England, and here it feels very much like the opposite of the Sunshine Coast. So although I'm jealous not to be with you in person, I hope you've all had a wonderful time at this year's competition. XTX Markets is a company founded and led by mathematicians, and we're one of the world's largest charitable donors to maths education and research projects. We're delighted to partner with the IMO and to support the IMO community through our charitable giving. Now, there are two programs that you may be aware of. The first is the Big Program. This is a scholarship program for IMO medalists to come and pursue their undergraduate study at top UK universities like Cambridge and Oxford. Now, this is a fully paid charitable scholarship, so you will never owe us a penny. We'll never ask for a minute of your time. We just want to support exceptionally talented young mathematicians to fulfill their academic potential. The second program is the Nations Program. This is for IMO team leaders and coaches to help you provide competitions, camps, and other training events for the young people that you support. You can find out further details about both programs using the QR codes on the coffee cups. Now, as well as supporting the IMO community, we fund several initiatives in the AI for maths space. One example is the Artificial Intelligence Mathematical Olympiad, better known as the AIMO Prize for short. This was founded in 2023 to spur the open development of AI models that can reason mathematically. And as you can see from the slide, we're supported by an advisory group including luminaries in mathematics, legendary figures in the IMO community, and leading machine learning engineers. The grand prize of $5 million will be awarded to the first open-sourced AI model that can achieve equivalent to gold medal standard at the IMO. And although progress is accelerating rapidly, we're not there yet. So each year, the AIMO prize runs what we call a progress prize, the first of which was won by Project Numina in 2024, and this year's progress prize was won by NemoSkills. And to tell you more about how the AIMO prize works, I'll hand over to the AIMO prize manager, Simon Frieder.
Thanks, Simon. The AI Math Olympiad is a series of high-profile competitions hosted on the Coyle platform. It's dedicated to solving Olympiad-level math problems with open-source LLMs. Because LLMs, as you all surely know, are rapidly becoming better in pretty much every domain, including mathematics, each round of the AIMO increases in difficulty. The first round of the competition, the AIMO 1, started in early 2024, and its level of difficulty was around the AIME, and AI here does not stand for artificial intelligence, but for American Invitational Mathematics Examination, as you all surely know. The winners of that competition received their award at the IMO last year in Bath, and for those of you present last year, great achievement, by the way, to be at 2 consecutive Olympiads. You might remember Team Numina receiving their award from our advisor, Terence Tao. Great pictures. We continued with the next round, the AIMO 2, last fall, and that competition ran until April this year. A team of researchers from NVIDIA called NemoSkills won that competition, and they'll speak about their winning model in a few minutes. I don't want to spoil things, but it's an amazing model built on top of a 14 billion parameter QN base model. If you don't know what it means, look it up and to give it a shot and see if your problem-solving skills are better than the model by NemoSkills. One important difference between the IMO and the AIMO is that our problems are stated in such a way that you have to devise a proof that in the end leads to a number between 0 and 999. And the reason we constrain ourselves to problems and proofs of this type is to be able to auto-evaluate the proofs that LLMs generate, because otherwise the AIMO would not be able to scale and support thousands of LLMs that were submitted. So thanks to the AIMO, we have open source LLMs that can solve Olympiad level problems, which is nice to have. But how does this competition really benefit the wider research around LLMs and their reasoning abilities? In the last few years, many public benchmarks of mathematical problems were created by various research groups, including myself. But unfortunately, there are a few problems with these. And you can think of a benchmark as a hill, metaphorically speaking. And models, as time goes by, try to get better and better, effectively hill climbing. And there's a vast landscape of hills out there. And to give you just one example, you have the GSM 8K dataset and benchmark, where GSM stands for grade school math. So these are really easy problems, high school level. And you can see a selection of open source and commercial LLMs that perform better and better on this benchmark. Essentially, nowadays, most LLMs can solve it. But the bigger issue here is that this benchmark, being public, as well as many other benchmarks, end up in the training set of LLMs. And this means that LLMs are thus contaminated with these data points. And evaluating an LLM on these same data points is not a fair assessment anymore. And while contamination is an issue that affects all public benchmarks in all domains, not just mathematics, for mathematics per se, a host of other issues exist related to Goodhart's law and as well as other issues that I won't go into detail here, but you can check out the linked reference. The big issue that you have when you run a competition is that, at least regarding contamination, that a competition eliminates this, because a competition is essentially a gated benchmark where you trade off the ease of evaluating your model against the problems from your benchmark being public. This comes, of course, at the price of you now having to manage an entire infrastructure that automatically manages and evaluates the models that contestants that participate upload. And this is where Kaggle comes in. Kaggle is a platform to run machine learning competitions. Can be any competition, doesn't really have to be about math and LLMs. And the way it works is that in our case, the host, which is us, send problems to Kaggle and a prize pot and a metric, how you can assess those problems. And Kaggle then splits these problems into a public leaderboard and a private leaderboard. The public leaderboard really shouldn't be called public because the problems from it aren't publicly available. It's rather something like a validation leaderboard, where as the competition goes on and candidates submit models, you can see almost in real time which model or which team gets which score. And the reason to have a split of problems into a public and a private leaderboard is that as you submit stuff to the public leaderboard, you will, as a problem or model creator, get some information how many problems your model was able to solve. And this leaks just a tiny bit of information about your problems. And to eliminate this issue, to win the competition, your model has to perform well on the private benchmark or private leaderboard. That is used as the way to assess the winners. And to summarize our competition, you can see here the 50 problems from the public leaderboard. And you can see for each problem some dots and some bars. And the dots represent the models. And if you count the dots, you can see that the winning model by NemoSkills solved 34 out of 50 problems. And if you drop actually the restrictions that NemoSkills set in place to make sure that it runs on Kaggle, and you evaluate this model on better hardware, it actually solves 36 problems, which is a really nice score. All Kaggle contestants combined almost solve all the problems. And if you look at the bars, this is a longer discussion, and there's not enough time here for details, but we will release more information. Just in a nutshell, the bars represent percentages of the models that submitted the 10 most frequent answers. That's the first 10 bars from left to right, and the 11th bar, which is either gray or blue, represents the remaining percentages. And to give you just example, the journey problem, the correct answer there, denoted in green, is the third most frequent answer that competitors submitted. So now it's time to check out NemoSkills' winning model. Over to you, Igor.
Hi, my name is Igor, and I'm going to introduce you our first place solution to the AI Mathematical Olympiad Progress Prize 2 competition. Before going into the details, let me introduce the full team. We have 7 people on the team in this competition, and all of them are listed on this slide, and we are all from NVIDIA. So here is a high-level summary of our solution. We start by curating a high-quality data set of challenging mathematical problems. We then generate so-called long reasoning solutions for these problems using a large language model. In this case, we use DeepSeek R1. You can't really use this model during inference in the competition itself because of the hardware constraints. So instead, we train a much smaller language model, Qwen 2.5 14b, on the outputs of this big teacher to try to mimic the style of those solutions. So this already gives us pretty good model, but to improve the results further, we teach this model to combine long reasoning in natural language with Python code execution so that the model can use Python whenever it needs to do some calculation. We then serve this model efficiently using TensorFT-LLM with FP8 quantization and speculative decoding techniques. And at inference time, we run multiple parallel generations and pick the most common answer as the final answer for each problem. So let me give you a little bit more details about some of the steps here. So to curate this high-quality data set, we primarily use problems from artofproblemsolving.com community forums. So the forum where people discuss competition-level math problems. Here is an example of one of the discussion forums. To process data from that website, we have this fairly complicated pipeline that consists of multiple cleaning and filtering blocks. So each block in this diagram corresponds to one call to an LLM with a particular prompt that helps us to do this task. For example, here is a prompt that asks an LLM to extract all problems from the forum discussions. And then we have prompts to classify questions, to extract answers, to decontamination, and all the other steps here. To give you a rough idea of the dataset size, we start with about 600,000 raw discussions on the forum. And after all the filtering and processing, we end up with about 500,000 unique mathematical problems that we can use for training. So now let me show a little bit of details for how we teach the model to combine long reasoning in natural language with Python code executions. This is typically called tool integrated reasoning, or TIR. Here is an example of one such solution. So you can see that the model goes through the solution using natural language first, and then it decides to write a small Python script to do a simple calculation, and then it uses the output of that calculation to continue solving the problem in natural language. And it can do so multiple times during the solution. So the main problem is, how do we teach the model to output solutions in this format? We did have a very good reasoning model, DeepSeek R1, that could do reasoning in just natural language. And what we wanted to have is this high-quality data set that interleaves natural language and Python code execution. So the natural thing to try is we can try to just instruct this reasoning model to use code. So just ask it to give us data in this format. But that doesn't actually work, because these reasoning models, at least the DeepSeek R1 we used at the time, is so heavily tuned on the particular solution format that the instructions just don't work. The model just don't follow the instructions you put in the prompt. So what we do instead is we fine-tune a very good instruction following model, Qwen 2.5 32b instruct, on a very small set of reasoning samples. So this way we get a model that can do reasoning not as good as DeepSeek R1, but still can do long reasoning, but still follows our instructions. And this model we can now just prompt to use code, and we get a big data set that roughly follows the format. It interleaves natural language with code execution, but it's not high quality. The solutions are fairly low quality. So what we do next is we apply aggressive filtering, which again employs multiple LLM calls to get a much smaller but high quality data set. In fact, here we remove about 99% of all the samples. And then we can repeat this process multiple times. We train a new model on this data, we generate new data from that model, and then we filter this data to make it even higher quality. Finally, we end up with a fairly big data set that's very high quality for this long reasoning TIR generations. So after we train the models on this data, we achieve state-of-the-art results in different model size categories. So we trained 4 different models, and the model we used at the competition was a variant of the 14B model shown on this slide. And we open sourced everything we did during this competition. We open sourced a series of OpenMath Nemotron models that were state of the art at the time of the release. We released our full dataset, OpenMath Reasoning. We also put all the code needed to reproduce our results in NemoSkills library, which is the main framework that we use in this competition. And we published a paper with more details. So you can follow the link on this slide if you want to learn more. Thank you for your attention, and back to you, Simon.
Thanks, Igor, for that excellent presentation of NemoSkills' solution, which was a clear and deserving winner, not just in terms of model performance, but also the quality of the materials that were written up and open sourced at the end of the process. Now, as you might expect, it takes something a bit special to beat thousands of participants in what is potentially the most lucrative prize ever run on Kaggle. Rather than me try to explain that, I'd like to use some of the words of NemoSkills' fellow participants and competitors, who said, "An incredible solution, truly worthy of the name state of the art," or "This year's first prize is even crazier than last year's," or "I never saw a Kaggle solution that took so much talent, skills, effort, and resources." So with that, and on behalf of XTX Markets, I'm delighted to announce that NemoSkills are the winner of AIMO Progress Prize 2, and as well as the kudos of the mathematics and machine learning community, are also the recipients of $262,000 in prize money. So we'll see you again next year for AIMO Progress Prize 3, which promises to be another step up in terms of the knowledge frontier. And the last thing I'd like to say is, again, congratulations to everybody who's taken part in this year's IMO, especially to the students, but also to the team leaders and coaches and volunteers who make all of this happen. So congratulations, thank you, and see you again next year.